Hello everyone, we are T17 and we are showing the analyzer and redesign of our electric mincer. Our chosen product is our electric mincer. It grades meat and soft food through a screw knife system, driven by a compact motor. Users simply load the ingredients into the hopper and turn on the device, and the machine produces a consistent minced texture without manual effect. We focused on two customer groups. Household users prioritize convenience, hygiene, and easy cleaning. Small restaurants require large capability and higher durability. To support manufacturability evaluation, we assume an annual production volume of 15,000 units. This assemble CAD serves as the baseline for all subsequent analysis. The fast diagram breaks the main task, grading fully, into feeding, crushing, discharging, convenience, and safety functions. This structure helps us understand which functions are core mechanical ones and which relate to user experiments. This matrix connects each function to the components that perform it. For example, the screw and knife handle crushing and the torches transmission. The hopper controls feeding, and the shell and bottom plate support safety and stability. This mapping reveals which components are functionally critical, and which mainly support convenience or protection. It becomes especially important when selecting modules, improving assembly, and analyzing cost. Based on the different needs of household users and small restaurants, we create a simple product family. The table on the left summarizes difference in bench size, durability, outlet requirements, hygiene, and appearance. On the right, we classify components into shared platform parts and variant modules. Most structural and mechanical components, such as motor, gearbox, screw, knife, and housing, remain shared to reduce tooling cost. Variation mainly occurs in the hopper, outlet geometry, and shell thickness to satisfy different capability and durability levels. This structure allows two product variants with minimal additional manufacturing complexity.
In this slide, we show the baseline manual assembly analysis. The product was assembled entirely by hand and documented in Table 8. The bottom plate and footpads were selected as the platform level assembly focus. For the module level, we chose the cutting plate and front cap nut. And next, I will introduce the improvements. First, for the cutting plate, we merged the cutting plate and the front cap nut into one pre-assembled cutting module, eliminating repetitive pick and align steps. This directly applies DfA1, and we removed the external layers on the cutting plate, improving its rotational orientation, ambiguity, and enabling symmetry assembly from any angle following DfA6. And we slightly enlarged the plate diameter, allowing self-locating insertion without secondary adjustment, applying DfA10 and the DfA11. And then for the bottom plate, our main structure platform, we unified the radius of all screw holes to allow one common fastener size and reducing variability in tool and part selection. This follows DfA2 and DfA5. And we also removed redundant locating holes and kept only fully necessary positioning features, cutting unnecessary alignment steps aligned with DfA11. And finally, for the footpads installed into the bottom plate, we converted their geometry into a chamfered insert press interface, enabling fast lead-in insertion without post-fastening or adjustment, applying DfA10 and DfA13. After redesign, total assembly process improved by 22.5 seconds, mainly due to part consolidation and easy orientation. Assembly efficiency increased slightly from 46.58% to 49.67%, indicating reduced non-value-added handling while keeping most functional integrity.
Using the DfA tables, the original outlet mode had 5 handled parts and a total automated assembly cost about 44 cents per module. The irregular housing, small seal, and the threaded nut dominate the handling and insertion cost. After DfA, the new model had only 3 handled parts. All parts are easier to feed, and we replaced the long threaded engagement with a short buoyant motion. The recalculated automated assembly cost drops to about 25 cents per module, roughly a 39% reduction. Functionally, the grinding and the discharge performance is unchanged, and the smoother geometry is actually easier to clean. So overall, this DfA automated redesign achieves a meaningful cost reduction while preserving the performance of the machine. In the original design, these were 3 main parts: a separate vertical feed tube, a complex outlet housing, and a threaded nut with a loose seal. This works functionally, but it was not friendly for automated assembly. The housing had an irregular shape that is difficult to orient in a ball feeder, and the nut requires a long screwing stroke and a precise regular alignment. After DfA, I combine the feed tube and the outlet housing into a single T-shaped molded part. The threaded nut is replaced by a quarter-turn buoyant ring, so assembly becomes a simple push and twist operation in the Z direction.
This redesigned cutting module combines the cap nut and the cutting plate into a single stainless steel part. We consider several processes, but only CNC machining meets all requirements: the 0.1 mm tolerance, the thin perforated region, and the surface finish below 1 micron. Because of these geometric and accuracy needs, machining is selected as the primary process. Before DfM, the design used 2 separate parts. This caused extra setups, more machining time, and unnecessary material. DfM Pro also flagged sharp internal corners, non-standard hole sides, and external locks that didn't contribute functionality. At 50,000 units per year, the analytical machining cost was about $8.40 per part. With DfM applied, we combined the 2 parts, removed the locks, increased fields, and standardized hole sizes. These changes simplify tool passes and reduce material volume from 40 to about 31 cubic centimeters. The updated estimated cost is around $7 per part, saving roughly $1.40. Hub's quotations for both designs were extrapolated to 50,000 units. The trend matches the analytical model. The cost drops from around $8.4 to about $6.9. The small difference comes from Hub's small batch pricing. Overall, both results confirm that our DfM changes effectively reduce machining cost.
The redesigned plastic part is the bottom plate of the meat grinder. The key dimensions are for the screw holes for mounting the motor in the upper part of the machine. The part is made with polypropylene. To meet the requirement of manufacturing this part, the possible manufacturing process compatible with polypropylene are narrowed down to machining and injection molding, out of which injection molding was selected. The bottom plate has the attributes of the chart at the top right with the total volume of 122.32 cubic centimeters. With the feature of the plate, the cost is calculated to be $4.65 per part. Most of the part comes from the tooling cost, particularly the cost due to the threaded holes needed to mount the upper part of the machine and the motor. DfM has suggested multiple ways to reduce the cost, such as minimize wall thickness, uniform wall thickness, and adding draft angles, though we can only implement some of them due to the design requirement. After taking account of the DfM recommendations, the team redesigned the part by reducing the overall wall thickness, adding some draft angles, and removing some unneeded features. The total cost has reduced by $0.15 per unit. As many of the features on the plate cannot be changed without changing other parts, the total improvement is limited.
For this section, we introduce a product service system designed to enhance the long-term value of electric mincer while improving customer experience and reducing environmental waste. Our first element is the blade replacement subscription service. User receive new cutting component on regular schedule, and when they return used blade, they earn store credit, which helps support the recycling loop and extend the product service life. Next, we support user through a smart companion app that track usage, send hygiene and cleaning reminder, and provide video tutorial and weekly recipe suggestions. This helps prevent misuse, ensuring consistent grinding performance, and keep the overall experience convenient and user-friendly. For commercial users, we provide a dedicated restaurant service program, including routine performance check-ins, priority component replacement, and potential collaboration with the meat supplier or reach more professional kitchens. Finally, we offer a structured warranty plan, 1 year for a household user, and extended 3-year option for restaurant, to reinforce reliability and reduce long-term ownership risk. Together, these services transform the mincer from a standalone appliances into a supported, sustainable, and service-oriented product ecosystem. For our final slide, with the DFA redesign, we improved assembly process by 22.5 seconds, increased the efficiency from 46.58% to 49.67%, and reduced outlet module cost from $0.44 to $0.27. DFM changes also lower manufacturing costs from $8.4 to $7 per module. For our critique, cleaning is still somewhat difficult due to internal corner. The design depends heavily on purchased motor and gearbox unit, and there is currently no built-in feedback to guide user maintenance. Looking ahead, our new approach includes simplifying interface, improving cleanability, exploring semi-custom drivetrain development, and adding basic sensor for predictive maintenance. These improvements would enhance manufacturability, reliability, and overall user experience. Thank you.